shadows from nonlinear accretion of scalar field dark matter, I would say, onto a black holes. So I basically spoil all of my talk. So basically, our motivation is to study how the size of a black hole and, for instance, how the shadow of a black hole will change when this black hole is accreting any kind of matter. In particular, we will concentrate on scalar field matter. Of course, our motivation is to try to model scalar field dark matter. This is very specific model of dark matter. It's very simplistic. Of course, there is a lot of models that try to introduce some kind of equation of states, astrophysically, there is also models using particles, for example, any kind of different particles. In our case, this is a scalar field with, well, this is massless scalar field, and this is coupled to the gravity weakly, okay? So we will solve Einstein-Klein-Gordon equations coupled during the evolution. And then we want to see how, of course, how the black hole is growing and how the shadow is affected during the evolution. We will use, of course, the EHT observations for M87 and Sagittarius A star as our observable. So we will compare the shadow size and also the photon ring size, because we can compute these quantities, these observable quantities from theory, so from Einstein theory. So if you remember here, this is M87, the first image from 2017. We have now new observations from 2018, and we have 2021 observations, but still not available for the publicly available. So we have also Sagittarius A star. So one interesting thing that we can see and confirm is that in both cases we can see a shadow that is this depression into the emission. So you can see here this region. We see in this way because we have low resolution. This is our best resolution ever to observe at 230 gigahertz with EHT. And then another interesting feature that we can see is the photon ring. No, of course we cannot see it clearly because we need infinite resolution. No, but after reconstruction, we can see that with this resolution from the EHT, we can observe this kind of photon ring. Of course, we have more features into the morphology of the image because we have an accretion disk. This is what we believe that we have. We have an accretion disk. We have, for example, in the galactic center, we have clouds and stellar winds that are contributing to the accretion. And then we have this kind of brightness emission also due to the Doppler effects, to the rotation of the black hole. But it's beautiful because we can test our gravity and plasma models also. Okay, just to say some like general characteristics of the image. So we have for M87, we have that it's our best model is telling us that the black hole is a spinning black hole with 0.5 spin parameter. This is a dimensionless parameter, but we traduce this to the speed of light. This is 25% of the speed of light, okay? So it's very highly rotating. We have also magnetic fields close to the black hole in the accretion disk from 1 to 20 Gauss. Of course, for people who is doing neutron stars, this is very low, but for us in supermassive black holes, this is high magnetized plasma. And then we also can estimate the electron temperature that is around 10 to the 9 kelvins. Also, this is the plasma, very, very hot plasma we have around the black hole. 10 to the 9 Kelvin, yes. It's very hot, yes. And then we have also the electric vector position angle. So basically, people are using also polarimetry to measure what is the morphology of the magnetic field close to the black hole. And of course, theoretically, we predicted long time ago that the morphology of the magnetic field is in spiral, no? And for M87 or scenarios where we have a jet, so basically the jet is, well, the magnetic field is going in spiral in the jet, okay? So we know this, I don't know, 10, 20 years ago, theoretically, of course, no? Now, this is the people from EHT who are doing this reconstruction of the image, they use this technique and then we can confirm that this is basically what we predicted from the theory. Okay? Another interesting feature from the theory is that we can estimate what is the size of the photon ring in terms of the gravitational radius of the black hole. Okay? And then this is between 4.8 to 5.2 gravitational radius. Okay, this is coming from the theory. When we assume that we have a Schwarzschild space-time, this is 5.2. And when we increase the spin of the black hole, then the photon ring size is decreasing, okay? Purely assuming general relativity, okay? If we assume another theory, then this can be changed. And okay, this is just to say that we confirm that this is what we predicted, no? The size traduced to the sky coordinates is 40 microarcoseconds, and basically we confirm the same size in both observations. And now in it's 2021, 2028, sorry, but also we measure again the image and maybe we'll confirm or not. Maybe this year we will have the new image. Well, you already know the EHT collaboration. I don't want to say more about this, but only that we had actually the EHT collaboration meeting last year here at the Institute of Astronomy, and we have young people basically taking a very quick course about what we are doing in the EHT, and there are very young people, so master and PhD students. Okay, now what we are using, which equation we are solving to study the accretion of the scalar field. Basically, so we're starting from the idea of the 3+1 decomposition. This is, remember that we always look in the beautiful Einstein equation that it's every teacher who is showing us the first time this equation telling us. In the left-hand side, we have gravity, okay? Geometry of the gravity. And then in the right-hand side, we have the connection to the matter, okay? Basically, yes, this is the Einstein equation, but it's very compact in the covariant way. So we want to have evolution equation, okay? What we are doing, we know that the space-time is one single manifold that is four-dimensional. Then we want to decompose this manifold in three space hypersurfaces and one coordinate that is temporal, okay? So this is the diagram that we are doing, basically. So this is the three-dimensional hypersurfaces, and then this is the temporal coordinates. So basically, we are doing a sandwich, a lot of sandwiches of the space-time. So then we rewrite the Einstein equations into this formulation, to this decomposition. Of course, we will not do that here, but then we obtain the evolution equation to the Einstein theory, okay? We have an evolution equation for the components of the metric. The metric then, this 3 metric is telling us how we will move into this three-dimensional space that only has spatial components and connected to a extrinsic curvature. Okay, so this is how the three-dimensional space is deformed. And then we have also an evolution equation for the extrinsic curvature in terms of the alpha, that is the separation between the hypersuperfices, and then we have this quantity that's, again, this is extrinsic curvature, defining how a normal vector in this three-dimensional space is moving, okay, is changing. And also, we have terms related to the momentum and to the density of the matter, okay? This is the connection to the matter, any kind of matter. And also we obtain a constraint equation that should be satisfied along the evolution, okay? This is very simple. People know this like ADM formulation of the Einstein equation, this due to the Aronowitz, Disser, and Misner formulation. So we want to solve this equation, okay? Apparently it's very easy, but we have here 16 components. We have 16 components also for the metric and extrinsic curvature components, okay? Again, I will not enter into the details, but it's very important that this kind of equation satisfy the hyperbolicity during the evolution of the equations, because we will have a stable set of equations, okay? And then we have to impose some initial condition to this, and these extra equations are part also from Einstein equation, so should be satisfied. Then, okay, so this is purely geometrical equations, and then we have the connection to the matter, okay? This is a gauge condition similar to the electromagnetism, because these two parameters are free. So basically we can choose whatever we want, whatever morphology we want into this 3+1 decomposition, okay? The only condition is that we want to have horizon penetrating coordinates into this two-dimensional surface that is the event horizon, because if we don't have it, then we will have singularities in our equations, and numerically this is a big problem. Okay? So for the scalar field, we have then no, we can do it. We can solve the Einstein equation inside of the horizon. Of course, this doesn't has any physically meaning, but we can do it because this is regular equations, okay? So what we are doing inside of the horizon is to applying an excision, okay? And then we just could, let's say, 90% at the 90% of the size of the event horizon, okay? And of course, this is complete set of equation. And if you see here, we are not defined any coordinates, okay? It's free of coordinates in principle. But in our case, in our problem, we want to solve very simple equations, so set of equations. So we will choose spherical coordinates, and then we will solve a non-rotating black hole. So it means that theta and phi components we will lose these terms, and we will simplify a lot this equation, okay? Because it's very difficult. Okay, also regarding to the formulation of the 3+1 decomposition, we have this hyperbolicity condition, but only for the spherical symmetry and for 1D. If we go out of this, then, for example, if we add rotation to our black hole, then we will lose this validity, let's say, for the equation. And then we will need another formulation. And we have like 2 or 3 more new formulations, like to keep this hyperbolicity, basically. I will not say more because it's a lot of equations, okay? So for the scalar field, then we want to have this effective Lagrangian and with this this potential, effective potential for the scalar field. As I told you, we want to simplify our problem because it's more easy to solve it in computationally. So we will choose massless scalar field. So basically we have zero potential. And then we will solve, of course, if we put the Lagrangian into an action together with the gravity, we can do the variation respect to the metric and then to respect to the scalar field, and then we will get Einstein equation plus Klein-Gordon equation, okay? So basically the connection to the space-time is that this equation is defined in terms of the, well, this, the Allenbertian is defined in terms of the metric, okay? And then we can write, after doing the variation, we can write a energy momentum tensor of the scalar field in this way, okay? So after doing explicitly this calculation, we have then, this is the Allenbertian, and then we have the metric terms that is coupled to the space-time. Then this is a second order equation. We have to solve this kind of equation for people who knows a bit of computational physics. We know, and numerical methods, we know that it's very difficult to solve a second order equation, okay? So what we are doing is to decomposing this second order equation in two equations of the first order, okay? And then we can solve it. So basically this is the evolution equation now for the scalar field. And here the nabla then is connected to the space-time, no? To the curved space-time. Okay, remember that we had some terms in the right-hand side of the Einstein equation. So here are explicitly written, okay? So then we can connect, if you remember, just to remember, to these equations, okay? And this source term to connect the space and the space-time and matter. Okay? Now, assuming that we have spheric Schwarzschild space-time, we are proposing a profile for the scalar field. So this scalar field is a wave packet of scalar fields. So we have to think in the physics in this way. So we have a black hole in the center, it's non-rotating black hole. And then we have a wave packet at some radius, okay? That is R0, and with some width, so that is this sigma, okay? And then we have to solve this A and sigma are free parameters. So we introduce this into the Einstein equations, into the constraint equation, and we solve this elliptic equation at the initial data, okay? As I told you at the beginning, we have to impose that we have horizon penetrating coordinates, and we have Schwarzschild-like equation, Schwarzschild-like space-time. And then if we assume this, okay, we have these components for the theta component of the metric and R component of this extrinsic curvature, okay? This is by imposing that we have Schwarzschild-like. Why I say Schwarzschild-like is because we will modify by introducing the contribution from the scalar field, okay? Then, yes, so we solve these equations. We solve equations for R components and theta components of the extrinsic curvature, and then now we can start our evolution. Okay? After showing the results, let me move this. Let me see if I can do it. Okay, I know it's a lot of information for the space-time. Do you have questions? Preguntas? ¿Todo está claro? Okay, we have to spend a lot of time to reach to these two sets of equations, okay? Uh, but we have to do at some point once per in our career. Okay, now let's assume that we have our space-time, we have our scalar field, and we solve Einstein equations, okay? That's fine. Now, what is the next? How we can construct a shadow or an image of the black hole? Well, maybe I have to clarify that we always say an image, but the image that I showed you before is composed by the shadow of the black hole, that it was in the middle, the obscure region in the middle, by the photon ring, and by the emission from the accretion disk, okay? This is the image. Okay, how we can extract the electromagnetic radiation from our simulations, okay? This is the question. So we are using this code that it's called Osiris. It was developed with my master student in Colombia at Universidad Industrial de Santander and my colleague Fabio Lora. So basically it's, well, I would say very simple for people who knows how to solve a geodesic equation, okay? What we are doing, so we are here. We have, this is a very beautiful example, and people has to do this test for new codes. So we have in the middle, in the way of this image and and us, we have a black hole, okay? So then we have to think that all of the rays, the null rays or the light trajectories that are coming from this screen are reaching to us, okay, to our telescope. So then we have to solve geodesic equations, okay? These colored lines represents geodesic equation. I will not show here. No, I will not show here. So basically, if you remember, for people who still don't take a relativity course, so what is the geodesic? What it means? So we have, well, let's go to do it simple. So the shortest distance from 2 points in the space-time that doesn't has any mass distribution is the straight line, okay? So it's exactly the same, but now in the curved space-time, okay? So now they are not curved if we see in an extra dimension. So we are doing this kind of line. So this is geodesic. Geodesic trajectories. It's happening also in the Earth for the flights when we take long flight. We are following the geodesic equations, okay? The geodesic motion, sorry. Okay, so because we want to follow the light trajectories, we have to solve we call null geodesics, okay? And then, of course, again, I am not showing here because it's maybe boring for us, but we are using numerical methods to solve this equation because it's not so easy to solve it analytically, okay? So basically we are, well, for this specific code, we are using Fortran, we are using Runge-Kutta to integrate in time and to integrate in space. So we are discretizing our partial differential equation using different finite differences. And then regarding to the Danny's question, we are starting our analysis from 0.9 times the event horizon inside. So we are basically inside of the black hole. And then we are arriving to ATM. So this is gravitational radius. Okay, it's far away for us because the black hole is small. Okay. Then what we are usually doing in the EHT or in our project is that we have fixed space-time. This is the difference between our previous work, okay? So we solve the ray tracing or the geodesic equation in a fixed background, okay? The space-time is not changing. It's basically fixed. And it's very important and interesting because we are modeling supermassive black holes. So we know that supermassive black holes are evolving from the early universe, no? Okay, this is important. But we assuming that this is fixed. So this is very big assumption in our calculations, okay? But now we will solve the same equation, so the geodesic equation, into the dynamical space-time. Yes.
If the space-time is fixed, why taking from the theory of the event horizon?
Uh, yeah, maybe I don't understand.
Horizon and measuring the time evolution. But if the space-time is fixed, why taking from the interval?
Okay. No. What I am saying is that if we fix the space, well, okay, let me reward what I said, okay? So I said, what we usually are doing, okay, when we are solving the geodesic equation to construct synthetic image of the black hole or the photon ring is that we assume the space-time, that the space-time is fixed, okay? But not here. Here, what we are doing is to solve the Einstein equations, okay? Now we have this point, okay? This is just to describe the code that we have. The code can solve the equations for fixed and for dynamical spacetime. This clarify your question or? Yes, exactly. I will show now. I will show you now. Okay, so then another important thing is that, of course, we can choose the number of pixels. It's very simple because we have single image, okay? And it's very cheap. So we can do it in our computer. But what happens if we want to generate millions of images? So then it's not so convenient. But for now, here we choose very high resolution in our images, and we choose this field of view because we are concentrated very close to the black hole. Only another clarification. So in this code, we are not solving radiation transfer equation, okay? This is very simplistic scenario where we only following the light trajectories, and basically we are using exactly this screen. So we put these colors, and we go to the other side and capture the light curves that are arriving to our detectors. Okay, so we are not solving radiative transfer equations for this case, of course. For EHT, yes. Okay, more questions? Okay, so then this is an example of the evolution of the scalar field. So here we have our black hole. This is for time, for the initial time. Then we have located our wave packet at 20 m, okay? And then we just leave to the Einstein-Klein-Gordon equation evolve it. And we have then different times. So this is 22 m, 26, 40, okay? What we have, because we have a wave packet. Usually when we have a wave, we have two modes, okay? One moving, in this case, one moving outside, one moving inside, okay? So this is usual behavior of a wave. Of course, this wave that is moving far away from the black hole can escape, and because this is scalar field is moving with the speed of light, so this mode will arrive to the null infinity, to the space infinity, okay? What happened with this mode, the second mode, is that is accreted by the black hole, okay? Then in this way, we can win mass of the black hole, okay? At the end, we can observe that here, for example, this packet, this wave, or this mode of the wave is going close to the black hole. Here is very close, entering into the event horizon, and here it's disappeared. No? and then it's accreted. Now we can measure how the black hole mass increased. Of course, because we are doing numerical methods, it's like mandatory to perform this kind of test. Okay, it's called a convergence test, because we have to show that we are getting in our numerical simulation is physically correct. Okay, so then we used to say quickly. So here we choose 3 different resolution of in our numerical evolution, and then we measure this second set of Einstein equations, that it's a Hamiltonian or energy constraint and momentum constraint. And we see that when we increase the resolution of our numerical simulation, then the errors are decreasing. Okay, so basically it's to believe in our results. Okay, yes. Do, do you mean here? Okay, nice question. So we have evolution equation of Einstein equations, okay? And then we have constraint equation, okay? So constraint equation should be 0, okay? So this is analytical expression. So we only call energy constraint because it's appear an energy in a right-hand side term, but should be 0, okay? So basically what we want to have here in this test is that this curve that is L2 norm of the constraint is going to very small values. So if we can have infinite resolution, then this should be 0, both quantities, okay? So it's not really related to a specific definition of energy. Nice, but we have to do this. So everyone who wants to do numerical simulation has to do this kind of test. Okay? It's just that we want to confirm that what we are getting is physically correct. Okay, let me then now kill this because we cannot see the interesting thing. Okay? So here again, I am showing the same evolution, but now we recomputed the image or the shadow, if we want to call it like this, for the initial time. So this is basically, we have here Schwarzschild black hole modified a bit far away where we added the scalar field, okay? Then it's starting to accreting. So we see that the the apparent horizon is increasing. Now we have at the end of the evolution, very big black hole, okay? Still Schwarzschild-like, so it's not non-rotating black hole, but now the apparent horizon is increased, okay? So here we can see the track of the apparent horizon, okay? We see that this is the apparent horizon is growing when the mode of the wave packet is arriving to the black hole and is accreted. And then after that, we have like steady state region, okay? Why? Yes. Okay, here, yes, if we translate this to seconds, it's very few seconds, hours, let's say, because well, here we see this axis is time, but this is in m, in mass of the black hole. Okay, this is what we are doing usually in our simulations. And then if you see here, so between let's say 20 and 40, actually 20 and 25, no 30, sorry, 30, 20 and 30. We have that all of the scalar field is accreted, okay? So before that, we have like almost partial. After that, we have a modified, let's say, no? A new black hole with new mass, but it's arriving to the steady state. So after 40, we can say that we have a stable black hole, okay? And then we can evolve this for a long time if we want. So for the reason we consider only 200 m. This is in time, but in code units. Okay. So what are you looking here? So if you see here these curves, so basically all of the bunch of curves are going to the same point here. So what is this? Someone recognize this? So this is again null geodesics, okay? So this is like trajectories. What we learn from our GR lectures is that if you send a light close to the black hole, this will be accreted, okay? This is what it's telling us. So then the light curves, the light trajectories are very important because it's showing us where is the location of the apparent horizon of the black hole, okay? And in this case, we want to be sure that this is stable, okay? Then this is the evolution of the black hole. Now, we can measure the size of the photon ring, okay? That is this one. And then we can also track during the evolution, okay? This is the size of the apparent horizon. And then this is the size of the photon ring, okay? So basically they are correlated because we increase the size of the apparent horizon, then the photon ring size is also increasing. Linearly in this case, because this is a non-rotating black hole, okay? And then, of course, this is interesting. Even we have 1D, we have spherical symmetry. It's very interesting because it's the first time that we are tracking how the size of the photon ring or the shadow size also is changing during the time evolution. And this is due to the accretion of the scalar field that we believe that we can model dark matter with this scalar field, okay? So for the reason is we say that, or we think that this is interesting because in this way, again, indirectly, we can try to have some insights of the dark matter, okay? But it's very simple, so we have to assume that this is very, very simple model. More question up to here? Yes, again, this is very simple. So this is scalar field, massless scalar field with no potential. So it's no potential in the Klein-Gordon equation, and it's very simplistic. So basically here we have a lot of possibilities to improve our model. The first one is to introduce the rotation of the black hole. The second one is to put massive scalar field. So, and there from previous results, we have some constraints, like observational constraints from other observations, that the mass of the scalar field should be 10 to the minus 22 electron volts. We can maybe introduce this by introducing the mass. And then we can also model different potentials of the scalar field. So we have a lot of things to do here. Okay? Yes? This one or this one? Say it again. This one. Okay, this is the apparent horizon, and this is the light trajectories that are going outside or inside, as you want to see, from the apparent horizon. So basically, you are sending from infinity. You send a bunch of the photons, okay? And these photons, because the black hole are going to the apparent horizon, and it's, of course, they will be accreted. And then here, it's because you can send, as you know, the geodesic equation you can send to the right or to the left. Okay, so basically here, this is also we call ongoing, outgoing geodesics. But also, what will happen if you send outgoing geodesics inside of the black hole? They cannot escape, right? What is the end of this trajectory is to the singularity, okay? So this is what is telling us. And we are using the null geodesics to localize the apparent horizon, okay? This is common practice. This is 0, yes. Yes. So basically we are in the border, okay, of the event horizon. Let's say 1 centimeter inside, we send outgoing geodesics, and 1 centimeter outside, we send outgoing geodesics again. We are fine. We are exactly, yes. Why? Well, it's a tricky because we want to track what is the evolution of the apparent horizon. Yes, are moving outside a bit here, are moving outside. If you are a photon, you believe that you will escape, but because the strong gravity and you are accreting, so you are not escaping. Okay. Yes, yes, exactly. Because the size of the horizon is growing. Of course, the gravity is also a bit more intense. Yeah, if you have 3D, you will see circular trajectories around the black hole. Exactly, exactly. Yes. Now, as a trick, we put only the geodesics that are escaping, okay? Because we can see it. This is the way. Another way is to solve this equation, okay? In 1D, it's very easy, but in 3D, it's not so easy. So it's better to use the null geodesics for us. It's more easy. Okay. So my master student, I forgot to tell you her name. Jennifer did like 100 simulations about changing the amplitude of the wave packet, also the width, and then we have this plot. So basically, here we are reporting what is the size of the final photon ring after we arrive to the steady state in comparison to the initial photon ring size, okay, the Schwarzschild one. And then the idea is to quantify. Of course, we see how the apparent horizon is growing. We see how the photon ring size is growing. But this is like not quantitative strategy. So, but here we quantified how the photon ring will change when we change the parameter from the model of the scalar field, okay? And then we tried to introduce because we know what is the size of the shadow or the photon ring in M87 and Sagittarius A star. So we introduce it here, okay? So this first region is for Sagittarius A star, and the second region is for M87. So basically this region, or these values for the wave packet number are allowed if we want to model the shadow of Sagittarius A star of M87, okay? And it doesn't matter about the width of the wave packet, okay? So this is our result. It's very simplistic. I say always that we have toy model, but we started this with bachelor thesis. So I think it's a very nice project. And then now we want to generalize this model by introducing the different mass of the scalar field, different potential, as I told you before, and then maybe rotation of the black hole. But we need a more sophisticated code to do it, okay? And it's not so easy to start from scratch programming a new code. Of course, we have another scenarios that are more interesting and more, I say that is a bit more realistic, where we have a black hole and then we have stable configuration of scalar field dark matter. So this is called Hairy black hole solutions. But this scalar field dark matter is has toroidal morphology. Okay, we know that from Navarro-Frank-White we have some very specific profile. Of course, this is different, but this is what mathematics allows to do it for now. Okay. Yes. Yes. This is. I think people misunderstood the the concepts. This is not really. It's not really hair from the hair theorem. Okay. It's only because we have an extra component from the solution of the black hole. So basically, we have rotating black hole. Okay, spinning black hole, and then we have a toroidal in this way, toroidal morphology of the scalar field, and then this scalar field is co-rotating with the black hole. Okay, so basically it's like adding, solving Einstein equation with matter. Okay, and then, but of course, the easy way is to do it with scalar field. And then again, the motivation is scalar field dark matter. Okay, this is more realistic because now here the black hole is rotating. And now what we want to do now to really solve the radiative transfer equation is that we have to evolve baryonic matter. So basically we want to put here an accretion disk, magnetized accretion disk, evolve it, see how the turbulence, how the instabilities are developing, and how the winds are expelling from the surface of this accretion disk, or if we have, for example, a jet formation or not. And after that, we will perform simulation to compute the electromagnetic radiation from this system, and then try again with the image in order to try to see if we can identify some scalar field component into the image, synthetic image, no? Because we will construct from the theory and then we will compare with the observations. And we are doing this with my students. Well, almost all of them are my students. So, yes. So the way is to compare the jet power. So we can measure here, basically here from the evolved system, we can measure the kinetic energy, we can measure the electromagnetic energy and enthalpy energy, okay? Well, one contribution from enthalpy. And then we can measure the jet power. And this quantity is unobservable. So we have measurements from observations. In this way, we are constraining, let's say, our model. So we have to compare the observations and our models, and we say, okay, if the energy is too low, then this is, we have to throw away this model. And if it's more or less in the range, in the error bar, then we keep this model. In principle, of course, now, if we want to specify a source, we have, I know M87, but I know there is a lot of AGNs with JET. So basically, for us, we are using M87. So we have 43 gigahertz, 86, and millimeter to 30 gigahertz that we can use to do the comparison. But of course, we have all of the spectra, no? Near infrared, X-rays. We in the second scenario in the where we are solving radiation transfer equation, we can solve the equation for different frequencies. So basically, we can cover from radio frequencies to soft X-rays. Okay, this is what we can do with our code, and then we can do the comparison. Okay, so it's not only one frequency or one band, as you say, no. But yes, this is what we want to do now. The next, no, is more realistic scenario. Okay, so yes, as I told you, no, it's very simple model. So we explore the scalar field accretion on Schwarzschild-like black holes in 1D. And we perform hundreds of simulations to explore how the size of the apparent horizon is growing, and for instance, the shadow size and the photon ring. We have to explore different scenarios where we include the mass of the scalar field and to perform 3D simulations. But for this, we need another code. And we have it. So we have Einstein Toolkit that is a code that been developing by 30 years, I think. And now they introduced also the Klein-Gordon equation. So basically, if we want, we can continue in this direction. Okay, that's it. So please, more questions. Thank you. Sí, adelante, adelante. Pregunten.
So then what could be a good next step for doing because you mentioned that this was one of at least the first part of the talk. What would be like the first good next step if you want like to make it considering for example rotation as well?
I think the more easy way to go is to explore the massive scalar field and also different configuration of the potential, the effective potential, because we can do it in 1D and we can use the same code. Of course, if we want to go to 3D, then we have to learn how to use Einstein Toolkit and how to modify it to introduce the components we want to have in our astrophysical scenario. You can do it actually. The 3D simulations. Okay. Yes. Yes, 1D it's because we can neglect the theta and phi components. So we solve only the radial component, metric and also the extrinsic curvature. Yeah. For the metric and for the extrinsic curvature, yes. Of course, 3D, the Schwarzschild, no. Well, of course, this, let me move here. Of course, this other scenario is different problem, okay? The problem that I showed before, it's 1D only, and it's Schwarzschild, yes. Núñez y Leo Tapia. Ajá. Ah, nice. Well, this is the constraint equations, and this is the gauge condition. So we basically have to impose this, and the relation is coming from the Schwarzschild metric. So we know that in Schwarzschild in Eddington-Finkelstein coordinates. So we know that this relation is satisfied. And then we impose this condition in our simulations. Yes, you have to start from the action equation from Lagrangian, and you have Ricci term, and you have to do variation respect to the metric and respect to the curvature, and then you obtain the evolution equation and obtain constraint equations. So it's basically Einstein equation decomposed.
Set up the initial configuration of the scalar field. Is there any physical reason why you assume that it's like
a wave packet. Yes, there is no physical reason. So basically, we were trying to search like a optimal initial condition for the scalar field. And we found that people who are doing cosmology with scalar fields, they are using this configuration like a wave packet, okay? Maybe because they were motivated by the expanding universe somehow. But I am not sure because I was looking into the literature and I didn't find anything, basically. So you can choose whatever you want here. Similar to the Hairy black holes, or if you want to propose a new profile like Navarro frame white or modified Navarro frame white with self interaction terms, for example. So you can do it also. Mhm. It's not constraints. Yes.
You've got the observation from 1887 and thunderstorm
Uh-huh.
to given the possible Taylor dark field models to use simulations to try to constrain which of them are not viable, which are. Would it suffice just to run simulations with, say, or it's more, are there more physical constraints that need to be taken into consideration for simulation to be trustworthy enough to be able to sort of tell us which cosmological models might not be possible?
Yeah, for us, it's very simple. So we only know two observables, okay? We know, well, okay, maybe I have to add one. The first one is the mass of the scalar field from other studies, from other scenarios, they constrain to 10 to the 22, minus 22 electron volts, okay? This is independent measurement. Let's say this is coming from theory. And the second one is the shadow size and photon ring size. This is the only three quantities that we can use to compare our models, okay? Now, as I said before, so the models from the scalar field are totally free, so you can choose whatever you want. And basically, this is what people is doing now. So you propose a model, you have the observables, you have to compare. If your simulation are satisfying what you are observing, so basically, like when we are doing experiments, so you want to test your theory. If no, then bye-bye, just throw away, okay? This is the way that we are doing. Which one is the physically correct or more physically correct? We don't know. So this is like the open question, no, for the dark matter that we still don't discover.
Yes. Actually, read the shadow. Could- Couldn't that help constrain right now as it is the sort of models which might not be available depending on the mass or something?
On the mass of what? Of black hole or? Yeah, yeah. Well, it's basically, from your model, the image, the shadow, the photon ring is connected to the physical quantity that is the spin of the black hole, the mass of the black hole, the gravitational radius. So everything is connected. So it's already connected, let's say, consider it.